speak about Fourier Transform now. I'm going to prove the Linz theorem for A1. So K is going to be a finite field, say size Q. Is going to be T to some power, and L is going to be different than P prime. So A is going to denote the affine line over K. So we have something called the Artin-Schreier cover of A, which I'm going to denote by phi. I don't remember which symbols people have already used for various Rubinii. I'm sorry if this coincides with one of them. So this is just defined by x maps to x to q minus x. So this is a connected Galois cover. So it has this Galois group in this surjection from the fundamental group of A1 to that thing. And this is isomorphic to K. It's easy exercise in kind of Galois theory.
Z hat?
What?
Z? What?
This is
of pi.
Additive group of K. What? Yeah. Well,
yes, of course. I'm sorry.
Yeah, the Galois group of a connected cover always admits a natural surjection from right? So in particular, if we have any character chi, oh sorry, psi of the additive group of the base field, bar star, then we can compose and we get a local system on A1. Okay, so this induces a local system, which I denote by L of psi. Okay, so this is a rank one. Yes, let's see. Now, for every element in the base field, I can put psi sub x of y just to give psi of x sub y. Just for implicit notation. So now that this induces an isomorphism of K with from A to QL bar. So I mean, I'd really rather put here. Okay.
Stephan,
yeah.
Can you like, is it easy to give explicitly the isomorphism of the Galois group of phi with the K plus?
Yeah, sure. It's just addition. So this roughly takes A into the deck transformation that takes x to x plus A.
Okay.
Okay. So know that if you want to take q to the n, you can do the same thing over the field of size q to the n, and you also get a geometrically connected alpha. Okay. Okay. So now we can define the Fourier transform. So definition. So let's look at the following diagram.
Stephan.
Yeah.
May I suggest that you use the full white of the board so we can see?
Oh, I have no idea how to do that. Maybe if I put this. Okay, I think. Cool.
No, starting from the next slide. It's okay.
Yeah, no, that's fine.
Just
take a look now.
Okay, thank you.
Is this too small? Can you still read what's written?
For me, it's a bit small but readable. So.
Okay. Okay. So now we can define the Fourier transform. So you can look at A times A. So you have a multiplication map from that to A being a commutative monoid or something with respect to multiplication. And you have the two projections.
Multiplication is addition or actual multiplication?
Actual multiplication. Okay. So maybe let me just say here that I fix once and for all a non-trivial phi. I fix a non-trivial additive character on K. Okay. So I define the Fourier transform, which is going to be a functor from DBCA into DBCA. You can do either a Tal sheaves or Weil sheaves here, it doesn't really matter, as long, yeah, I think it's fine. So it is defined by taking a complex, say G, pulling it back along pi2. So all pullbacks are derived, all shrinks are derived, unless I say otherwise. Okay. Or maybe, do you want me to write R's, or should I not? Does anyone have any?
I'm against writing R.
Yes, please do not write
writing R's. Okay, wonderful. Easier for me. I'm gonna move a little bit. So what I'm doing is I'm taking the local system corresponding to the character psi that I fixed. I pull it back along the multiplication map. I tensor this with pi2 upper star of G. I push it down using pi1, and then I shift by 1. Maybe let me say what do I mean by shift by 1, just so there is no confusion. So that should be enough. So if I have a complex, I shift it by 1, then it's the thing that's in degree I, the original thing in degree I plus 1, which is the same thing as what Shaul denoted by suspension. Okay. Any questions so far? So this
Why would you do that, though?
Why would I do that? Good question. Let me say to you what's going to happen very soon. So very soon I'm going to tell you that the stock of the Fourier transforms coincides with some sort of compactly supported cohomology. Okay. Now I remind you that our goal is to bound the eigenvalues of the Frobenius acting on some compactly supported cohomologies. Okay. So this will allow us to reduce the statement, which is Dalin's theorem for A1, to the statement that the Fourier transform at most increases the maximal weight by 1. Okay, and this we will do with some just Flancherel formula and some like Fourier analysis.
I want to give a very, very quick remark, if I may. For those who are maybe not immediately see why would you call such a thing a Fourier transform, I just wanted to note that if you everywhere there's an A, you write R, and instead of shifts, you think of functions, and the function L psi is now the function that sends x to e to the 2 pi I x is the character, then and now you replace tensor with multiplication and lower Schrick with integral, you get the formula for the Fourier transform. Okay, so I don't want to take a lot of Stephan's time, but I just wanted to say.
Yeah, sure.
It does look like a Fourier transform.
Okay, maybe just a small lemma. I'm not even sure if I should say this. Whatever. So for every A and K, we have a map from A to A, which takes X to AX. Let's call it lambda A. Then if you pull back.
Stephan's screen is stuck.
Oh, my screen is stuck. Not good. 1 second. Let me try the name thing. Yep. Sorry, my iPad is stuck now. Okay. Can you see?
Yes.
Wonderful. So if you pull back along the multiplication by A map, the local sheaf L of psi, you get L of psi A. Okay? Just a small observation, which together with base change immediately implies the following thing. So this plus base change imply the following. So for every A of K, and let's write K in DBCA, we have the following. So the stock of the Fourier transform of K with respect to psi.
Can
At
you
point
keep
A.
calling it G because K is field and I don't know, it's confusing.
K is what?
K is already the
Oh,
field.
yeah. Capital K is the field. Sure. Okay. Yeah, good idea. So the stock of the Fourier transform of G at the point A is, we said, we don't write this here. Let me only here write this anyway, if you may. So this should be something like this. Okay? So in particular, if we want to bound some kind of eigenvalues of some kind of anything acting on compactly supported cohomologies, it suffices that we bound the eigenvalues of the corresponding thing acting on stocks of the Fourier transform. Okay? Now, maybe
What is written in there? I don't really understand. I'm sorry.
What? Sorry?
It's written the stock of the Fourier transform is what? Is
Maybe write the theorem on a new page, Stephan.
What?
Maybe write the theorem on a new page. I think it's better.
So this is the derived compactly supported sections of G tensored with L of psi A and shifted by 1.
Okay. Thank you.
So this just comes from you apply the proper base change formula to the definition of the Fourier transform that I gave, and you apply this easy computation, which I summarized in this lemma. Okay?
Stephan?
Yeah.
What is the category that G lives in? DC3A? DBCA, sorry. So this is derived bounded derived category of Tal or Weil sheaves with compactly supported with a constructible complex. Okay. So maybe let me remind you some things and put some notation. So we have a function from the objects of DBCA into, I denote this by F goes to maybe G goes to Fn of G, to functions from A Kn to QL bar star. Okay, that's defined by sending by this taking trace of the correct power of the Frobenius, something like n over the degree of x, probably stock P of x. Okay. So this is for sheaves. We extend this to complexes in the natural way, or you can just view this as being automatically for complexes if you interpret trace correctly. What is n though?
What?
What is n though?
N is a natural number. For every natural number n, I have a function on the kn valued points of the affine line.
Yeah,
This
okay.
is what I denoted by TR.
Yeah, so Shai denoted it like this, I think, right?
Except for the R being at the top.
Being
Yes.
n. Yeah.
And like superscript, not subscript.
So the reason I didn't want to choose T again is because I already denote the Fourier transform by T lower psi, and I don't want too many capital T's floating around in here. I thought about just doing checks for the Fourier transform, but you need to also keep track of the characters. So check lower psi already feels not very, I don't know. Yeah. Okay, so this is the shift to function correspondence. I remind you that it commutes, so F maps to Fn, F commutes with lower shrieks, upper stars, derived tensor products,
That's all I need really. Okay, so a corollary of this is the following. So so it turns out that the shift to function correspondence respects Fourier transform in the following sense. So let n greater or equal to 1 and g dbcx ca. Then fn of t psi of x is t psi of f, sorry, t psi g is t psi of f and g of x, which is by definition minus the sum over x in kn of f and g x psi probably inverse. It should be y. It's y. Okay, so this is just the usual Fourier transform on k or on kn with a weird minus sign that I don't know. I have speculations about where it comes from, but I don't know. Okay. So
Yes.
Kn is the nth extension of K, or is it?
What? Kn is the field with Q to the n, which I fix, like for every n, I fix a hierarchy of them containing. Okay. Yeah, any other questions so far? Whatsoever? Remarks, comments, I don't know, objections?
The only thing I think the x in the beginning should be like applied after you take the function, just to be.
Yeah, sure. Yeah. Okay, so a corollary of this. So this is a corollary of like shift to function correspondence commuting with everything. Corollary to this. Now, corollary to the corollary is that we have a Plancherel formula. Which says that the norm.
If this computation is
by
very
k.
short,
Sorry, 1 second. Is q times the norm of f, and k is g.
Q to the n. I mean, it's the size of, it's the volume of the group.
Yes. Yes. Yes, you're right. So I don't know if Ariel did this eventually. I think not. So let me say a couple of words about something that I thought would be done in Ariel's talk. So
wait, did we prove the Plancherel that for this you need on the shifts?
No. This is a formula. Once you know this, this is a formula for functions on Kn. This is like very.
Right. This is because it doesn't use
no shifts, no.
Yeah, you know okay. This. I agree. Yes.
Okay. So let me just remind another small concept. So we have this awful norm.
I apologize, since I came to the talk 5 minutes later. Can you define the norms?
The n norms?
Yeah.
Yeah, it's just when you take the product and integrate, like in sum.
Yeah, and what's the role of n?
It was defined in Ariel's talk. This is just like you have an inner product.
Yeah, but remind me what the role of n is.
Consider points in the degree n extension.
You're looking at points of degree n over the base.
Okay.
For all n.
Yes. Okay.
So if you can package all of these together to define some kind of souped-up norm, which is defined by this awful formula that I'm going to write down in a second, and you can forget it in like half a minute. So this is the lim soup of the rows such that the lim sup over n of the square of the nth norm of f and g times q to the minus n rho plus dim x, which is 1 for us, is smaller than infinity. Okay, so I just define this object. All I care about it are the two following properties. I honestly don't need anything else from it, and this is why
Is this like Schwartz functions?
I don't understand precisely what you mean.
Okay, never mind.
Sorry, I'm kind of bad with technology. Yeah, so two properties of that thing that I'm going to need. One is that we can restate the Plancherel formula more nicely using this norm. It just says that the norm of the Fourier transform of G is the norm of G plus 1. Note that, let's look at this for half a minute. So Plancherel formula tells me that in degree n, I multiply by something like u to the n somewhere. Okay, so it's not very surprising by how this norm is defined that like making the Fourier transform will exactly increase this norm by 1. Okay, just by looking at this formula. Do you guys feel more or less comfortable with this?
It will come from the log, right? In the definition.
Yeah, exactly. It's like completely, there's nothing fancy here. Just like you.
Okay.
It's very immediate. So the second thing, which I'm going to kind of black box, which kind of appeared at the end of Ariel's talk, was that if G over a smooth curve is mixed, and tau mixed, I fix the tau once and for all also, and has no compactly supported section, so this subset, then this norm just coincides with the maximal weight. Okay, so again, I'm gonna completely black box this. I don't understand this statement very well. I believe it had something to do with some analytic properties of various cell functions or something either. But I'm just gonna use this. Okay, I think now we're ready to actually prove the theorem. So let me just remind you what it says. So theorem. So assume we have an open embedding of an open subset of A1, and F is a smooth, pure sheaf on U. And let's denote by rho the corresponding representation. Phi 1. I'm going to need this. I'm going to put this aside. And we assume the following things. So assume that 1, F is geometrically non-constant.
Just to orient everyone, Stephan is now stating the theorem I ended my talk with. The theorem we still have.
Yeah, I'm restating the theorem that Shaul reduced the original formulation of the Linz theorem to. So 2 was that F is wait, sorry, sorry, I'm doing a very bad thing. So 2 is going to come before 1. And 1 is geometrically reducible And you can even assume that it's étale, not that it's gonna matter, I think. You should correct me if I'm wrong, but we can assume this in any case, so you might as well. And 3 is that f is unramified at infinity.
You already assumed that it's smooth.
Yeah, but I'm saying it's étale.
What does
And
étale mean?
and that it's geometrically reducible. Étale, I mean not a Weil sheaf.
Yes, we can assume it by shifting the weights.
Yes, I can assume this. I don't think it's gonna matter much for the proof in any case. But one really, when I refer to one later, I mean that f is geometrically reducible. 2 is that f is geometrically non-constant, and 3 is that f is unramified at infinity. Okay. So now the proof is going to go as follows. I'm just going to claim 3 things about the Fourier transform. The theorem is going to follow immediately from those 3 things, and then we're going to prove these 3 things. Okay. So
just a small question because I don't have a very good memory. What is unramified at infinity?
It means that the corresponding, you can think about this way. It means that the corresponding representation of rho extends to pi1 of u adjoin infinity. So it means that.
You can also say that the sheaf extends to a smooth sheaf.
Okay, it's factors for pi1 of the. Okay, great, thank you.
Yeah. Okay. Yes. Okay. So I'm gonna put G to be J lower shriek F. I want to have a notation for this. And maybe then temporarily denote the Fourier transform of this by H. Then we claim 3 things about H. So 1 is that H is concentrated in degree 0. You can kind of, I guess, think about, I guess no, I don't want to say anything about things that I'm not familiar enough with. So the second thing is going to be that H naught completely supported of H vanishes. And third thing, maybe let me call them ABC, because I already have 1, 2, 3. Is that the Fourier transform of this guy is mixed. Okay, so let's assume A through C
We
for a
don't
second.
see your.
Oh, you don't see my screen?
Yeah, it got stuck again.
Okay. Can you see it now?
Yeah.
So let's assume A through C for a second and prove the theorem. So then we know by the formula for the stocks of the Fourier transform, we know that the stock of the Fourier transform at 0 is just H1 compactly supported of A1 with coefficients in G. I think I might need to twist here somewhere. Let's think about this in a second. It's the same thing as the compactly supported sections of F. So
I'm sorry again. What is F and G? Like
F is the original sheaf on U. G is the lower shriek to A1.
And H is.
And H is the Fourier transform of that.
Okay, great. Thank you very much.
So let's look for a second at our base change formula for the stocks of the Fourier transform. Yeah, here. So if you want to compute the stock of the Fourier transform at 0, and we already know that this thing is a sheaf, it has no global sections, then the only relevant thing happens in 1 degree, and I think we do need to twist by L of psi, right? Maybe.
But the stock is at 0, no? So psi of 0 is 1 or something.
Oh, correct. Thanks. Sorry. Yeah, exactly. Thank you. Yes. So we need to bound eigenvalues of some Frobenius acting on this guy. So it therefore, it's enough to prove that the maximal weight of the Fourier transform with respect to psi of G is at most the weight of G plus 1. Okay. Now this is just going to be some magic tricks. So both G and tau psi G satisfy 1 being tau mixed and 2 having no compactly supported sections. Okay, so for G, we know that it's tau mixed because this is by assumption. Okay, and we know that its compactly supported cohomology is 0 because it's a local system on an affine thing. So its compactly supported cohomology vanishes. And for the Fourier transform, we know this by properties B and C beforehand on the left. Okay, so from this, it follows that by the thing that happened in Ariel stock, it follows that the weight.
Wait, why do we know tau, like tau psi of G is mixed? You only assume. Property C doesn't say that the double Fourier transform is mixed?
Oh, no, sorry, this is my bad, thank you. G.
Oh, okay.
Yeah, sorry. Okay, so combining these two facts, for both G and T psi G, and a statement from Ariel stock tells us that we can compute the weights of the Fourier transform as the norm because it's mixed and it has vanishing compactly supported cohomology and it's a smooth thing. So no, we don't need smooth, just mixed. We don't need smooth. It's a mixed thing on a smooth curve with vanishing compactly supported sections. So we have this equality. But now by Plancharel, we have that this is the norm of G plus 1, which is by the exact same thing from Ariel stock. This is the weight of G plus 1. And the proof is basically finished. Okay, after proving A through C.
Didn't you say it's an inequality and you proved equality? Oh.
So for maximal weights, there's actually inequality.
Okay.
I believe so. Okay, so let's start proving A through C. So basically, so C is basically just gonna be the same trick with the real sheaves. To prove that it's mixed, we're going to prove that it's we're gonna take a real mixed sheaf, which it's a direct sum and off, prove that the Fourier transform of that thing is and so forth. Yeah, so this is going to be the strategy of C. I'll do this in detail later if I have time.
That should be obvious already from the L function, or no, the L function doesn't determine necessarily the.
For B, I'm going to maybe I want to have a small interlude about Fourier inversion. Let me just state Fourier inversion. Because it will be needed for B. B is basically just apply Fourier inversion and you get, and this formula for computing the stocks of the Fourier transform, and you immediately get what you want. So this says that the Fourier transform with respect to psi inverse applied to the Fourier transform with respect to Phi of G is G twisted by like plus minus 1.
I think it's -1.
I can never tell with these things, but I think you're right. Yeah, -1. Thanks, Shower. Okay, and like most of the content of the proof is going to be to prove A. A is really the big thing. maybe. I guess maybe you can think about A as in some sense being analogous to, like, if you have functions that are vanishing at infinity rapidly enough, then they have the Fourier transform is sufficiently regular or whatever. But, like, this is just philosophy and not anything precise.
Is it like you said that the Fourier inversion gives you B? Like
what? Yeah, Fourier inversion gives B. This implies part B. Yes.
Why is that?
I will do this later in more detail if I have time. But essentially, like, you can compute the zeroth compactly supported cohomology as some cohomology of a stock of a Fourier transform. And then you can do like an inverse Fourier transform kind of thing, and you get much.
Yeah, okay.
Yeah. I'll do this soon if I have time. But I want to focus on A because this is like where most of the content is. Okay? So we want to prove that the sheaf is complex of sheaves is concentrated in degree 0. It's enough to check that the cohomologies of its stocks in degrees different than 0 vanish. So let's take some point. So it's enough to check that H not compactly supported of J lower shriek F tensor L psi X vanishes, which is, by the way, the same as H not compactly supported on U of F tensor L psi X by the Leray spectral sequence for lower shrieks or something, which is kind of degenerate in the case you have an open immersion. Okay.
Wait, what are we proving now? I'm confused because the letters changed.
I'm proving part A.
A is that it is concentrated in degree 0. Great,
yes.
Thanks.
I hope this is compatible with. Yeah. Okay. Yeah, I'm proving that it's concentrated in degree 0. For that, I'm gonna just check it stockwise. Okay. So I want to prove that the 0th compactly supported cohomology vanishes, and that the second compactly supported cohomology vanishes. Which is again, by the same reason, the same as the second complex support cohomology of U with respect to this, by some degenerate Leray spectral sequence argument. It's enough to prove these things. Right, because in degrees other, like, bigger than 2 or smaller than 0, things will vanish for dimensional reasons. Correct? Do you guys agree?
What about H1 or something?
H1 is the one that's supposed to not vanish. It's supposed to be
yes, you move it. Yes.
And so all others will vanish.
Yes, concentrate the degree 0 after moving.
Yeah.
I'm fine.
Okay. So H not compactly supported vanishes because F is smooth and U is affine. And note that I'm just twisting by a character, so it's like it's still affine. It's still smooth. Sorry. Okay, so the main point is H2 compactly supported, which is what we're going to prove. So Poincare duality implies that the compactly supported H2 of that whole thing is the same thing as you take rho. So you take the representation on V corresponding to rho tensor psi X. This is a representation of pi 1 of U. And you take its co-invariance. Maybe just finish it with a bar. I don't know. Okay. Maybe I think like this is fine. Yeah, no, like this. Okay, so Poincare duality tells us that second compactly supported cohomology is dual to zeroth homology, which is fixed points, and dual is fixed points is co-invariance.
You ignore from the Tate twist because you don't care about it, right?
What?
You ignore about the Tate twist because you don't care, you want it to be zero, right?
But
Okay, so now assume that this thing is non-zero. And we want to get a contradiction. Okay, now let's see what we have. So by 1, which says that this thing is geometrically reducible, we know that this is the trivial rep of pi 1. Because if it wouldn't have been the trivial representation, being an irreducible thing, the largest quotient on which it acts trivially would just have to be 0, because it can't be the whole thing. Okay? You guys good with that? This is important.
I don't get, like, by which one?
Which what?
Which, you said by 1. What is 1? What does it mean?
1 is the assumptions of the theorems, that f is geometrically irreducible, that f is geometrically non-constant, and that f is unramified at infinity. I'm about to use all 3 of them in the following 3 minutes. Okay?
Mm-hmm.
So 1 is geometrically irreducible, 2 is geometrically non-constant, 3 is unramified.
Why is geometrically irreducibility gives you that
because geometrically irreducible means that this representation is an irreducible representation of the fundamental group, right? But I'm looking at the largest non-trivial quotient on which it acts trivially, and I'm assuming that it's non-trivial. But so by irreducibility, you must start off with the trivial one-dimensional. Okay? So, so now we divide into 2 cases: if x equals 0 and if x is not equal 0. So if x equals 0, then rho tensor psi x is rho, contradicting 2.
Two is that it is geometrically non-constant, meaning that the representation on the geometric fundamental group is not the constant representation.
Exactly. So if x is not 0, and this is where all of this unramified stuff are going to come in. So first know that so psi x is non-trivial. And rho is unramified at infinity. So, and rho tensor psi x is geometrically constant. Hence also unramified at infinity. Okay, because geometrically constant sheaves are unramified at infinity automatically. So
wait, I'm very sorry. In the case of x equals 0, why this contradiction?
Because we get that
rho is a trivial, and then
rho is trivial, but it's also non-trivial by 2, because 2 assumes that it's not geometrically constant.
Ah, right.
Okay.
Yes, thank you.
Cool. Yeah, I probably should put U bars here. I guess this is confusing, right?
Yes, U bars everywhere.
Yeah, thanks. I probably should have put U bars in some other places as well, but as long as no one's confused, then I'm fine. So in any case, we get that rho is unramified at infinity, and rho tensor psi x is unramified at infinity because it's geometrically constant. So we get that psi x is unramified at infinity. Okay, and I'm claiming that this is a contradiction. And I think I want to explain by a diagrammatic manner. Let's see what we have. We have pi. Let's do.
It's a very good place to have a new page.
This is not going to be a very big diagram. So if it's going to get too small and you can see what I'm writing, let me know. But I think it should probably be fine. Okay, so we start off with this character psi of pi1 of the Artin-Schreier cover phi, which is the same thing as pi1 is not correct, so Galois group of this. Okay, now we have the inclusion map from A to P1, which induces this one to pi1.
Stephan, let's do it on a different page.
Okay.
Let's do it on a new page. Deserves the page.
Sure. I think I'm going to use about the same amount of room though, but sure. We have this character that we started off with. And we have this surjection from the fundamental group of the affine line to the Galois group of the Artin-Schreier cover, right? Now we have the inclusion of the affine line into P1, which induces a map from pi1 of A1 into pi1 of P1. This is the same as pi1 of spec A, because the projective line has no non-trivial covers, kind of. We have also this map, which is the trivial map. Okay. And now we have just said that psi extends to pi1 of P1. Right, so psi unramified implies the existence.
What do you mean by the trivial map there?
I mean, I don't know a lot of meanings for the trivial maps between two general groups.
I mean, why does it commute?
Why does what commute?
You've drawn you've drawn a bunch of stuff, and then you've drawn this zero.
Oh yeah, you're asking why does this triangle commute?
Yes.
I think one of them is geometric and the other is
because this
magnetic.
well commutes, if you wish. Does this help at all? Like the map here, all of the maps to spec K coming from the projections to the base field, and the Artin-Schreier map is a map defined over K. So all maps to spec K commute, right?
Okay.
But then this one is an isomorphism because of coverage.
Yeah, okay, okay.
This is a good point. Do you understand? Is this clear?
I mean, the Galois group is a group of Dex transformation of this cover, right?
The Galois group of phi.
May I just make a very, I'm going to make a small remark. It might be helpful. So just to make it clear. So what Stephan's doing here is kind of a careful diagram chasing, which is a good thing to do. But just to explain the upshot, yeah, the upshot that our character really came from a Galois cover of A1, and saying that this thing is unramified is just saying that this Galois cover extends to P1. P1 doesn't have any Galois covers. That's what's going on here. You know, then
Except for
you make argument diagrammatically, but that's what's going on. If it's unramified, you can add this point at infinity. There's no covers of P1.
Mm-hmm.
That's the entire point.
But there are also no covers of A1.
To deal with geometric fundamental groups, and then this is
the point is also that it's geometrically connected.
Wait, so I just want to no, the A1 has a very large non-trivial.
Sure.
Right. Thank you.
Which is exactly what we used when we
constructed. The Artin-Schreier, yes. Thank you very much, Tomer. Really helps.
Okay, is everyone happy with this? So we have finished proving property A of the Fourier transform.
for this specific.
I have a small question. Why is it of pi1 of A and not A1 and not pi1 of U? Like, how do you?
Because the character is defined on all of A1. And the character is already unramified everywhere.
Ah, the character is defined.
Yeah.
So what happened that we have the representation on U?
Well,
we have the representation on U, and it comes from a character on A1. That's the magic, right?
Yeah, the character comes from A1 from the beginning. And at this
no, but the representation comes from U, and because the tensor product is. Oh, okay, very, very cool. Okay, thank you.
I use the representation to show that the character is unramified to infinity, and then I just completely forget about it.
Very.
So this was part A. Let's prove now part B first because it's really quick. So by the Fourier inversion.
It's currently stuck again.
Oh, it's stuck again. Yeah. Let's see if I can reconnect. Sorry guys, I'm very technologically uninclined. Wait a second. Yes, sorry for the technical difficulties. Okay. Can you guys see?
Yes.
Cool. But by the way, let me know if I start going too much over time. So by Fourier inversion, we know that the compactly supported cohomologies on A of H, which was the Fourier transform of G.
Just remind us quickly what is this? What it is that you are proving?
What? Oh yeah, thanks. I'm proving that the thing has no compactly supported section. The a priori complex, which we have now just proved that is in fact a sheaf, has no compactly supported sections. Okay, on A1 or equivalently on U. No, sorry, on A1. I guess. Correct me if I'm wrong. Yeah, and stock at 0. So I'm using the formula for the stock of the Fourier transform and Fourier inversion. Okay. So this is the same thing as like the -1 cohomology of the deep psi inverse of deep psi G tensor L phi at 0. The same as just this of G tensor L psi inverse. Yeah, -1. This is a take list. And this is 0 just because this is a sheaf. Is maybe concentrated in the user. Are there any questions about this?
Yes, can you say again what the second equality?
So the second equality is just the definition of H.
Ah, yes, thank you. And the third is the Fourier inversion. And
First is Fourier inversion plus like base change. the stock of.
So B used A and Fourier inversion.
Yes. Yes. And again, proper base change, but like proper base change is used almost like it's used more frequently than it's not used. I don't know. Pretty much everywhere. So let's prove C maybe, and then if I have time, I might say a few words about proving the Fourier inversion formula. The only black box I left, I think. So again, as I said, this is just going to be the same, like real sheet.
So let us be reminded by what is C.
Oh, C said that the Fourier transform in our case is mixed. Yeah. So let's take an element in QL bar star such that tau of it is Q to the omega. Omega was the highest weight, or just D weight because it was pure. So we define H isn't that letter already. Can I use a capital K, or will that be confusing?
Yes, that would be fine.
No, that would be confusing.
What? It's a capital K. It's a cal K.
I don't think that small k is going to appear anymore at all. So am I allowed?
If you promise that, then
I can promise that. Okay, cool. Thanks. Yeah, I'm gonna use capital K. Thanks. So this, I remind you, is like pi to upper star j lower shriek f tensor m star l psi. That's the thing that you should push with pi 1 to get a Fourier transform, right? And I'm gonna sum it with its dual tensored LB, as we always do. Well, I remind you that LB is the Weil sheaf corresponding to the Weil smooth sheaf that corresponds to the one-dimensional representation of Z that takes.
Stephan, don't you want to sum F with its dual tensor LB and then apply the Fourier transform and then check that it's real?
So
how do you know that the resulting, like, how do you define now B? Because you don't know this thing is even pure. So
no, the weight omega is the weight of the original sheaf.
Okay, maybe this is the way the proof goes. I'm just confused.
Follow.
Just continue. Just continue.
Okay. Yes. So we prove, like in A, that that the Fourier. This is what I want to say. Wait a second. I think I just want to say that both of these things are concentrated in degree 1, both of the things that I sum. Is that true? I'm just sorry. So both T psi of J lower shriek F and T psi inverse of J lower shriek F check are concentrated in degree 1. So we know that, like, we only care about, like, the first derived functor of pi 1 lower shriek. All of the others will vanish. Again, as in A, like, we reproduce the same argument and use this. So now, so K is tau real. And we have the Grothendieck formula. So both of these imply that this guy is tau real. So it's tau mixed. So the Fourier transform of G, which is a summand, is also tau next.
So just to orient everyone, the thing that this arrow that if k is tau real and Grothendieck formula implies that R1 pi is Schrick, this argument, there's an argument there that Stephan isn't saying. It's the same argument I used in the
Yeah, sure. It's like what happens in Shaul's talk.
Yes. It was the argument, if you remember, that when we proved that the weights are correct, we used the fact that it's a ratio of polynomials, which is real, and we have bounds for the weights, and then the roots should be different, so we get real for everything. That was the kind of argument that also appears here.
Shai, how long do I have left?
Almost 20 minutes.
Oh, wow. Okay, I might finish ahead of time. I thought I'm going to finish much earlier. And okay, let me say a few words about like Fourier inversion. You need some preliminaries, but let me just say a lot of things and stop me if you're kind of suspicious about it. So phi is still denoting the Untitled cover, okay? So first thing I'm saying is that this is smooth of rank Q. In fact, I can even say more. Psi star of QL bar is the sum over all elements of K of L of psi X. Okay. This can be seen, for example, from the fact that the corresponding representation of the fundamental group is like some kind of group algebra or something like that over the arcade. So let me not get too much into it. Okay, this is kind of where it comes from, if you want. Yeah, so should I remind the statement of Fourier inversion, or do you all remember it?
Yes, remind please.
Okay, so it says that T psi inverse composed with T of psi applied to G is G twisted by -1. Okay. So let me say proof in quotation marks. So maybe first we need to compute some things. So we want to compute cohomologies of all sorts of things like L psi. The first thing to notice is that, so we know that the computation that maybe should have been done at some point in this workshop is that this is 0 and that this is 0. I'm not going to prove this now, I'm just going to black box this. This might sound believable if you're familiar with the ordinary topology on the complex numbers or something and believe very strongly that the Tal cohomology should imitate Betty cohomology or whatever. So, so by Lie, so Lie spectral sequence implies that same is true for the push forward by phi. Which in turn implies with this fact that so let's put lemma that H1 of A.
I don't know how I don't know how to like. Feel free to not answer this, but like, is it what is the Lie spectral sequence? Or
what?
Like,
I think maybe we can talk about it afterwards, but I think for the purpose of this talk, when he says Lie spectral sequence, he means he composes two functors. And
yes. Yes.
It's
like,
Stephan ways of
if I would have used, if I would have written everything in terms of infinity categories, this just means like functoriality, if you wish, of something, right? But yeah, I don't know if this is helpful, but
okay.
Okay, so we managed to compute. So
just because the push forward of QL bar decomposes like this, and we have vanishing for these push forwards, we get vanishing for first compactly supported or not cohomologies of all of these L psi x. Okay. Now let's again continue with the proof. So the main point is that we can now compute.
Stephan, I'm very sorry. What are you doing right now?
I'm trying to prove Fourier inversion, or at least say some
Okay.
things about Fourier inversion.
Okay. And what did you explain by now?
Let me just write some things.
Okay.
One thing and then answer your question. I explained about half of what I'm writing at this time. Okay. Can you see what I just wrote?
Yes.
So the compactly supported cohomology is on A of QL bar is 0 in degree in non-zero degree, and it's QL bar twisted by -1. Yeah, in degree 0.
No, I mean in degree 2, maybe.
Yes, probably in degree 2.
Yes. Yes, of course. And sorry, this should not be QL bar.
Oh, wait, in that case, I'm not sure that this is true. I said it for QL bar.
Why?
Because for QL bar, the second cohomology is QL bar -1 and all the other vanishes.
So you're asking about the I equals 2 case, right?
No, my correction was for the QL bar, but then you should change the QL bar to something else, and I don't know if my correction stands, so I want to say this.
Let's see. So we have just proved this for I equals 1, right? For I smaller than 0 or bigger than 2, everything vanishes anyway. So the only cases of interest are 0 and 2, right? I think. Yeah, so 0 is also not a problem because this is a smooth.
L of x is smooth, so H0 will be 0, compactly supported, and on-pair duality will give the H2, right?
Yes, exactly. Yes, thanks. So now, using this computation, you can prove certain orthogonality relations. So, using computation of this. We get, I can show that if you take the Fourier transform of the constant shift, you get a delta function. Let's see. -1. Again, this form might not be super surprising to people who are used to, I don't know, any kind of Fourier theory on non-compact things, whatever, I don't know. Okay, so now let's proceed to how the proof goes roughly. So so the strategy of the proof now is basically just going to be to apply the base change theorem 3 times and the projection formula once, and we just get what we want. Okay, let me just say to what diagrams do I apply what and stuff. So we have this diagram. All diagrams now are going to be Cartesian. This is pi 1, 3, and these are beta and alpha, which I'll write what they are in a second. We also have another diagram like this. So here, alpha takes x, y, z to y, z minus x, and bx, y equals y minus x. by base change of these two, we get some very, very ugly formula for the inverse Fourier transform of the Fourier transform. So we get something like
it seems like alpha has too many entries in the term, in whatever it's.
oh, sorry, yeah, thanks. This should be z minus x, no comma. Thank you. Thank you. Okay, and you can check that both of these diagrams are commutative and even Cartesian, so we have a base change formula. And if we write down what the base change formula for both of these will give you, which I'm not going to write R as per Shai's request. So the pi 1,3 lower shriek of pi 1,2 upper star of n star L phi psi inverse. Tensor, I'm sorry, I'm continuing with this because I just don't have enough room. Pi 2,3 star, m star L psi. Is the same thing as the push forward along the diagonal. QL bar minus 1 shifted by 2, minus 2, sorry. Okay, so if you carefully enough apply the base change theorem, do I need to take anything derived? Probably not, because the, okay. Yeah, okay. Now, by base change for another diagram, so maybe I'll just unwrite it too. So now, third diagram is just projections. We have A3 to A2 to A2, A1. This is pi 1, pi 2, pi 2, 3, pi 1, 2. So this is again a commutative, even a Cartesian diagram. So base change for this gives some even nastier formulas. So let me start a new page. So I'm just gonna use the previous thing and this base change. So I get this even nastier formula for the inverse Fourier transform of the Fourier transform. This is like R pi, no, R pi lower shriek 1, pi 1, 2 lower shriek of pi 1, 2 upper star of m star L psi inverse. Tensor pi 2, 3 star, sorry, parentheses should start here. Pi 2, 3 star, m star, L psi. Tensor pi 2, 3 star, pi 2 star, g. All of this shifted by 2. If you just apply base change 3 times to the correct things, you get this long ass formula for the inverse Fourier transform of the Fourier transform. And then if you use, sorry, I think if you use now base change for the third thing, for the third diagram, goes to the projection formula maybe a couple of times, or maybe just once. Check me, I don't remember. This ends up being something like this, which is already G of. Yeah, so this is not very illuminating for me, but I assume that, like, if you go over calculus proofs for Fourier inversion, for QP, or for R carefully enough and all real analytic details, you will get something that is very close to what I just said in kind of much decategorified way, I assume. I have not checked this.
I think something that I thought that you would do is prove first that, like, not you, because I know that the book doesn't do it, but I was sure that, like, maybe actually I should say it like after the.
No, I think I'm about done. Like I proved everything I wanted to say, I think. Anyone has any questions before we finish?
I have, I mean, maybe this is too vague of a question, but I mean, at least like for the most classical case of the Weil conjectures, which is maybe an elliptic curve or something like this, there is another like elementary way of proving it. It's just kind of using Jacobi sums to express the eigenvalues. Like maybe this doesn't work for literally every elliptic curve, but at least for some of them, and like for Fermat curves, things like this. And Jacobi sums are basically, I mean, they're like a product of two Gauss sums divided by a Gauss sum, and a Gauss sum is a Fourier transform, like exactly of this thing, like a Fourier transform for the additive kind of FQ of a multiplicative character. So I wonder, like, how do these two things compare? Like, because I mean, it's also a bit weird, like already in the elliptic curve case, that you see kind of the additive Fourier transform of A1, like appear in the formulas there. Like, I wonder if, like, this breaks down to the same thing. Like, what?
I have no idea, but if anyone has anything.
I can make two quick remarks about this. They're not going to be very precise because it's going to take too long. But one is, you can read off what's going on as a kind of generalization of the Jacobi sum perspective. So it does inspired from this in some sense. And regarding the weirdness of regarding the weirdness of the fact that you get some kind of a Fourier transform for the additive group, I'll just make one very simple remark, and you know, you can dwell a lot into this philosophy. But one way to think about so you can look at the number of points on elliptic curves in the following way. You have y squares equals some polynomial of degree 3, and you're just counting how many times this polynomial of degree 3 is a quadratic residue, and how many times it is not, because essentially that's right. If it's a quadratic residue, you have two solutions. If it's 0, you have one solution. If it's not, four solutions. And if you think about this, claiming that if you think about this polynomial of degree 3 as something that you know, as a map from FQ to itself distributes randomly with respect to the proper residue, then you would expect that the number of solutions would be more or less Q plus a sum of Bernoulli variables, and that's square root of Q, which is also indeed essentially what you get by this is indeed the Hasselbalch. So one way to think about, you know, how one possible perspective of how to get Fourier transform is from the same reason that you get Fourier transform when you're trying to give probabilistic bounds in additive combinatorics. It's the same kind of situation. You're trying to bound a certain additive random variable, and you're using Fourier transform to get the control. So it's a kind of a similar perspective.
Another cool analogy, but I don't know how can it be made precise if at all, is that like if you take just a local system, you can also do Fourier transform for local system, like Fourier transform for D modules on the affine line. So if you take like a thing with a monodromy alpha around the origin and you Fourier transform, then you get minus alpha minus 1, which is kind of this one. I don't know if it's like the same one, but it feels like the same one. No? We can't hear you, Tomer.
Let's talk about it later. Let's let Stephan continue.
I finished. Like, if anyone.
I think we're finished. Let's.
Wait.